Now, after that last example, you're probably thinking, wow, this is really, really cool. We are able to find the slopes of tangent lines of functions and find instantaneous velocities, instantaneous rate of change. That's amazing, and I can't wait to do more. And you may also be thinking, could we take this a step further? Okay, and the answer is yes. That's what we're going to do. Why would we want to take it a step further? Okay, maybe that's actually what you're asking at this point. Okay, so in the previous method, and let me go back and point to that formula again, right back here. We can find the derivative of a function at any x value, right? So we did this function at 1. And we did all this work, and eventually we got to an answer. Now, what if we took the same function, but we wanted the slope of the tangent line at a different x value, maybe like x equals 4. Well, we'd have to set up the whole thing again and put 4's in for all the a's, right? F prime 4. Limit h approaches 0, that's the same, but then we'd have f of 4 plus h minus f of 4 all over h. Okay, and it's basically a brand new problem. If we wanted to do the same function but at a different x value, we'd have to just start from the beginning again. And we're thinking, oh, I wish there was a faster way. Like, is there a way that maybe we could do something and find the derivative just one time, and then whatever x value we were interested in, we could just plug those numbers in, right? So if we wanted it at 1, we could just plug in a 1. If we wanted it at 4, we could just plug in a 4. If we wanted it at negative 20, we could just plug in negative 20. That would really be great. Okay, yes, exactly. That's what we're going to do next. I'm glad we're on the same page. Okay, so here we go. The derivative of f of x in terms of any x. Any x. That's a little better. There's some shadows going on. All right. Here's what it looks like. All right. It's the same formula. One change. Instead of writing a, we just write an x. F prime of x equals the limit as h approaches 0. F of x plus h minus f of x all over h. Why does this do it for us, this simple change? Because before we were thinking of this as a particular number, right? A is a variable, but it represents one fixed value. Now you can choose that fixed value to be whatever you want, but it's a fixed value. When we say x, that's a different type of variable. X represents all x values at the same time. Okay? All right, I think you get it. Because we use variables this way ever since we started using variables. There was these two different ways of using variables, and maybe nobody ever pointed that out to you. No, they did not to me. But there's really two types of variables, right? There's something like x, which represents every number at the same time, and then there's like a or b, which are thought of as a fixed number. Okay, so here we go. And you notice the way we say it's exactly the same. F prime of x. Well, I said that a moment ago anyway. Okay, let's see the power. Here we go. We're going to go all the way back to that function from before. F of x equals 16x squared. All right, so we are asked to find f prime of x. So this will be the derivative in terms of any x. And really going forward, these are the derivatives that we're going to be finding in the course. So, for now, we're kind of referring to it as the derivative of f of x in terms of any x. But this is just going to be what we think of as the derivative from here out. Okay, so find f prime of x, part A, f of x equals 16x squared. So we're just going to apply our formula. All right, and you can see it there, right? The difference quotient. Now it's not hiding at all. There it is. And then we got this limit as h approaches 0 in front of it. Okay, let's do this. Well, it looks like I just repeated the formula. Never a bad idea. Just start by writing the formula again. Okay. And then I need to go to another piece of paper. And we will now apply this formula to our function 16x squared. And here it is. So on the side, we've got f prime of x equals the limit as h approaches 0. Always that. It's always that limit. And now, okay, f of x plus h. Well, as that applies to 16x squared, that would be 16x plus h quantity squared minus, and well, that's just f of x, so difference quotient, right? We just put the function in right there, 16x squared, in for the f of x. And it's all over h. Now at this point, you know, maybe some of you guys are feeling really comfortable. Oh, we practiced all those difference quotients. Perfect. This was the reason. That's why we were doing it. So when we got here, it wouldn't be new. It'd be something that we've been doing. And we can just knock this out. Okay. Next line. Let's get rid of this. F prime of x equals the limit as h approaches 0. Let's FOIL x plus h squared. That's kind of small, sorry. X squared plus 2xh plus h squared with the 16 in front. And okay, we're still just subtracting 16x squared all over h. Can't do anything with that. Now we will distribute the 16. And we can start to see this, how the cancellation will play out. F prime of x equals the limit as h approaches 0, 16x squared plus 32 plus 32xh plus 16h squared minus the 16x squared. Oh yeah, those cancel. And for what's left, they both have an h that we can factor. Okay. F prime of x equals the limit as h approaches 0. The h that we factored is going to cancel, leaving us with 32x plus 16h. And this is all just playing out right into our hands as it should. Finally, at this point, it's safe to plug in the 0 for the h. So all that gets multiplied by 0. And what do we have? F prime of x equals 32x. Now, I haven't mentioned this before, and I probably should have. At the moment you plug the number in, you don't write that limit as h approaches 0 anymore. When you plug it in, you're doing the limit right then. So then it's not part of the final answer. We don't write limit right here because we did it in the previous step. Okay. I don't think I mentioned that before, and if I did not, then it's overdue. Okay. I may have, though. All right, so f prime of x equals 32x. Now, check this out. 32x, I mean, that's just like any ordinary function. Right? 32x, okay. And it behaves like any other function. It's just, it represents slopes of tangent lines. So check this out. I crunched a few numbers here just so we could see the power behind this thing. Hey, we're going to start with f prime of 3. Now we did that back, right? That was the like the first example we did in this section. We looked at f of x equals 16x squared. And we said, hey, what's the instantaneous velocity at x equals 3? And if you remember, our answer to that was 96. Well, let's use it in this style. F prime 3, well, just like any other function, we're just going to plug the 3 in for the x. So 32 times 3. And oh, guess what? That's the 96 that we got before. You think, okay, that's kind of cool. You know, we reproduced an answer in a different way than we did earlier on. You know, all right. So what's the big deal? Because if we want to find the derivative value at some other x, we don't have to start the problem and do it all over again. We did it all right here. So if I want to find f prime 5, okay, 32 times 5. 160. There's the slope of the tangent line to this function at 5. How about f prime 0? Well, that's kind of a cool one. 32 times 0 is 0. Now this is kind of sweet. Remember the graph of 16x squared? It's a parabola, right? And it goes through the origin. The vertex goes through the origin. Hey, what does this tell us right here? Okay, at 0, at x equals 0, right there at the bottom, the slope of the tangent line is 0. Well, what would the tangent line look like there at the very bottom? At the very bottom, at that vertex, isn't the tangent line perfectly horizontal? It's just grazing by, going in the same direction. Yes, and what's the slope of a horizontal line? Well, 0, right? And okay, there's where it is. And we can we're kind of exploring a little bit now, but hopefully that's all clicking for you. Okay, let's do another one of these. We can't stop with just one. We're going to do another one. And you could argue this one's a little bit more challenging. Not that it's more steps, but the algebra is kind of challenging, so it's definitely good that we do it together. Now, the majority of derivatives we're going to be doing and things we're going to be working with in this class are polynomials. So things like 16x squared, right? That's a polynomial. Rather simple one. But we do want to get our heads wrapped around some other things. And, something like this, 2 square root x plus 1. All right, so part B, we're going to find f prime of x, the derivative function, you might call it, for f of x equals 2 square root x plus 1. Okay. Now to begin, we got to think back to that formula for the derivative, right? F prime of x equals, let me go ahead and write it because I don't think I wrote it on this one. F prime of x equals the limit as h approaches 0, f of x plus h minus f of x over h, the difference quotient there with the limit in front. Okay. Let's see this. I'm going to block a little bit. I'm going to block some of what I've written there. Okay, there it is. There's the difference quotient. In this case, f prime of x would equal the limit as h approaches 0, 2 times the square root of x plus h plus 1 minus 2 square root x plus 1 all over h. So this first part, right, we replace the x with x plus h. And this part, well, we always just repeat the original function, and it's all over h. Okay, so far so good. Now looking at that, that's kind of intimidating, right? So okay, maybe you can set it up. If you're struggling setting these up, then we definitely that's something you need to work on before you start actually doing the algebra. But if you feel good setting something like that up, then you got to think, okay, like what are we going to do to simplify this? Hey, we've got these square roots involved. We were practicing similar situations, and they weren't probably this much or maybe this intimidating, but we were practicing rewriting things with square roots. It's called rationalizing the denominator. We had a question like that on the first quiz. So let's see. How can we work with that same idea? So we're not rationalizing the denominator here. There's no square root in the denominator, but there are some in the numerator, and we're going to use the same approach. We are going to multiply the top and the bottom by the conjugate. Okay, so we're going to take what you see in the numerator and just turn that minus into a plus. And we're going to multiply that, and that's what I've got hidden over here, kind of waiting to be revealed. All right, let's center that up a little bit. So we're going to multiply the top and the bottom by the conjugate, but it's the conjugate of the numerator, which is a bit different, but turns out this is going to work for us. Okay. Again, still kind of intimidating. It's a lot to write, but let's see how this plays out. So, turns out it cleans up really fast. It seems like it would just become awful, but actually quite the opposite. All right, so again, we've got f prime of x equals the limit as h approaches 0. That's just being copied. Let's see here. When we FOIL, we got to FOIL these two numerators. So when we say this times this, well, what happens? Well, 2 times 2 gives us the 4, and square root x plus h plus 1 times square root x plus h plus 1 is just x plus h plus 1. If you multiply the same square root by itself, it's like it squares, and the square and the square root cancel. And we get simply this, x plus h plus 1. Okay. And if we keep, so that's the first times the first. If we keep foiling, hey, what's going to happen to the first times the last? Or we usually say that's the outside, right? In FOIL, multiply the outside. Okay, well, whatever that is, it's just going to cancel when we multiply the inside, just like when you rationalize the denominator. When you multiply by a conjugate like that, the two middle terms cancel out. So multiplying here cancels out with multiplying there. We don't have to do that multiplication. We can see it's going to cancel. One's positive, one's negative. And then finally, the last times the last, well, negative 2 times positive 2 is the negative 4. And square root x plus 1 times square root x plus 1. The square roots square when they multiply by itself, and we get just x plus 1. Okay. Now, if you're comfortable with the numerator, what's going on in the denominator? Okay. Don't distribute the h here. There's a reason why. Just write h parentheses and just copy that denominator. Do not multiply out the h. Just write h parentheses and copy what you see there. Okay. Trust me, done these before. Okay, let's move on. I know you're probably pausing to copy this stuff, but I'll leave that to you. As you can see, it's evening at my house. It's getting kind of dark here. Now let's look at this numerator. So it turns out some nice simplification, right? 4x plus 4h plus 4 minus 4x minus 4. The 4x's cancel and the plus 4 minus 4 cancel. All we have is 4h. And then we have that same denominator. We haven't touched it. The h is still sitting out there. Now here's why we did not distribute, because we get those h's to cancel. Cancel those h's. Boom, boom. Of course, the other parts get copied. And now we're really in business. Okay, at this point, I sort of saw that these cancel out, and I just went for it. I just went ahead and plugged in the 0 for the remaining h. So at this moment, I'm taking the limit. So I'm not going to write it anymore, and I just write f prime of x equals 4 over 2 square root x plus 0 plus 1 plus 2 square root x plus 1. And why did I write the 0? Well, there's a lot going on. Okay. And now, if you continue to work this out, well, this is square root x plus 1, and that's square root x plus 1. So 2 square root x plus 1 plus 2 square root x plus 1 gives you 4 square root x plus 1s. And then the 4's even cancel. For this particular example, it's just really, really nice. And we get f prime of x equals 1 over the square root of x plus 1. Okay. And we got it. There's a circle there. It's hard to see. That's our derivative function. So if we wanted to know the value for the slope of the tangent line, or if you're thinking of it as the instantaneous rate of change at any particular x value, what was our original function this time? 2 square root x plus 1. If you'd like to know the slope of any tangent line at any x value, just plug that x value right here and get that number. So for a lot of numbers, it's going to turn out to be some decimal, but you know, maybe if you plugged in like 8, you'd get 1/3, you know, for the whole thing, slope of 1/3. Okay. One thing that we should point out um, is that this thing is going to be undefined at -1, right? -1 would cause you to divide by 0. So I've got this note over here, f prime of -1 does not exist. You're like, well, that's kind of weird. I'll show you why when we see the graph, when I do the Desmos video when I'm all done with this. And it'll be pretty plain when you see the graph why that's true. But we can note it right now, right? Actually, any x value that would cause a negative under the square root, we don't deal with imaginary numbers in calculus. So any negative square root we would say does not exist too for the derivative. Okay, so kind of on this theme of derivatives not existing, we've got just one last thing to say. I'm going to save that for the last video.